Welcome, my dear students, who are going to study lattice energy. The energy released when gaseous ions are brought from infinity to form a mole of solid substance at 0 degree Kelvin is known as lattice energy or the crystal energy. It is a measure of strength of the ionic bond. Larger the lattice energy, stronger is the bond. For example, Na plus Cl minus in a gaseous state, it gives NaCl in a solid state. Delta H is equal to minus 769 kilojoule per mole. Delta H is the energy released when gaseous Na plus and Cl minus ions are brought from infinity to form a mole of solid NaCl at 0 degree Kelvin. This is the lattice energy of NaCl, and its numerical value bears a minus sign, which indicates that the formation of sodium chloride from its ions is exothermic. However, the lattice energy cannot be determined by the formation of a molecule from its ions. Therefore, it is determined by breaking the molecule in the solid state into ions in the gaseous state. This requires a certain amount of energy, which is exactly equal to the lattice energy. Therefore, lattice energy is also defined as the enthalpy change when one mole of a solid substance is converted into its ions in a gaseous state. Sodium chloride in a solid state, it gives Na plus and Cl minus in a gaseous state. The delta H is equal to plus 769 kilojoule per mole. Though delta H in this case has a positive value, the lattice energy of NaCl in solid state has a negative value. Lattice energy is defined as energy released when one mole of each of gaseous cations and gaseous anions are brought together from an infinite distance to form the crystal lattice of ionic solid at 0 Kelvin. The true or total lattice energy termed as U for a mole of the crystal lattice containing an Avogadro's number n, capital N, if units is given by U is equal to lattice energy U is equal to minus N A e square Z1 into Z2 upon R plus B upon R raised to N, where R is the interionic distance in centimeter, Z1 and Z2 are charges on the ions, E is the electronic charge, capital A is a Madelung constant, B is a constant, and N is a Born exponent. The Coulombic attraction due to the term Na E square Z1 into Z2 upon R, and repulsion due to the term B upon R raised to N. The constant B measures the strength of the repulsive forces, and it differs for different ions. The value of N Born constant exponent, N is a Born exponent, N varies from 9 to 12. The depending upon the ions in the crystal, usually N is determined with the help of compressibility data of the given crystal. Coulomb's energy V is equal to Ne square Z1 into Z2 upon R kilocalorie per mole. V is equal to 332.57 upon R kilocalorie per mole is equal to 332.57 upon 2.38 angstrom minute kilocalorie per mole. Is V is equal to minus 139.7 kilocalorie per mole, means minus 584.6 kilojoule per mole. Thus, the energy of a mole of ion pair Na plus and Cl minus in the gaseous state is 139.7 kilocalorie per mole, lower than that of the separated ions. The net energy change for the formation of the gaseous ion pair can be calculated as follows. Na in a gaseous state, it gives Na plus and electron, Na plus in gaseous state. The I is equal to 118.4 kilocalorie per mole, and Cl in gaseous state, accept the electron to form Cl minus gaseous state, E is equal to minus 83.4 kilocalorie per mole. Na plus and Cl minus, it gives the Na plus Cl minus gaseous state. The V is equal to minus 139.7 kilocalorie per mole. Then the delta is equal to minus 437.7 kilojoule per mole. Lattice energy depends upon the following factors: ionic radius, ionic charge, electronic configuration of the cation present in the molecule. Ionic radius, lattice energy depends upon the reciprocal of the interionic distance small r. The interionic distance r is the sum of the cationic and anionic radii in a crystal lattice. That is, small r is equal to r plus r minus, cation anion radius. Here r plus is the radius of the cation and r minus is the radius of the anion. Lattice energy will depend on 1 upon r plus r minus. It means that the lattice energy will change if the cationic or anionic size is changed. In a compounds where cations or anion is the same and oppositely charged ion is a change. For example, in the compounds of the sodium chloride, sodium chloride, sodium bromide, sodium iodide, cation is the same and size of anion increases. Or in the compounds of lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride and cesium fluoride, anion is the same and the size of cation increases. Then the lattice energy decreases. Therefore, amongst halides of the sodium, lattice energy for sodium fluoride is 898 kilojoule per mole, and for sodium chloride it is 769 kilojoule per mole. That is, with the increasing size of anion, the lattice energy decreases. Similarly, amongst alkali fluorides, when the size of the cation increases, lattice energy of lithium fluoride is 1037.6 kilojoule per mole. For sodium fluoride, it is 898.7 kilojoule per mole. The lattice energy becomes smaller as the anions becomes larger. For example, compound and the lattice energy kilocalorie per mole are minus, that is increasing, and R plus remains constant. That is for sodium fluoride, sodium chloride, sodium bromide, sodium iodide. Sodium is a constant, fluoride, chlorine, bromine, that can be changed. So sodium chloride has lattice energy minus 218.7, sodium chloride minus 185.9, the sodium bromide, the lattice energy minus 176.7, the sodium iodide lattice energy minus 165.4. The lattice energy becomes smaller as the cation becomes larger. The compound and lattice energy R plus increases, R minus remains constant. The lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride, cesium fluoride, fluoride is constant. The lithium, sodium, potassium, rubidium, that can be changed there. The compound, the lithium fluoride, the lattice energy minus 246.9 the kilocalorie per mole. Sodium fluoride minus 218.7, potassium fluoride minus 194.4, rubidium fluoride minus 185.9, cesium fluoride minus 178.7. With small cations like lithium, there is a considerable variation in the lattice energy with changes in the anion. Variation in lattice energy with change in the anion. For example, the element lithium plus kilojoule per mole and rubidium kilojoule per mole. Fluorine, chlorine, bromine, iodide. For fluorine, lithium and rubidium, lithium it has energy 1037.6 kilojoule per mole. For rubidium, the 784. If the element chlorine, lithium plus 862.7, then rubidium 695. If bromine 785.7, and for lithium, and the for rubidium 634.7. Element iodine, for lithium 729.7 kilojoule per mole energy, and the rubidium for that the 596.6 kilojoule per mole. Then ionic charge. If the charge on an ion is greater, the lattice energy is larger. The greater the values of the Z1 and Z2, larger is the lattice energy. Example MgO, where product of a charge is 4, that is Z1 into Z2, 2 into 2 is equal to 4, has much higher lattice energy than for any one the alkali halides lithium fluoride, for which the product of charges is only 1. Z1 into Z2 is equal to 1 into 1 is equal to 1. Similarly, Al2O3, where the product of charges is 6, Z1 and Z2 is equal to 3 into 2 is equal to 6, has even higher lattice energy, MgO minus 3795 kilojoule per mole, and for Al2O3 the energy minus 15,269.9 kilojoule per mole. Means magnesium oxide, it has the charge Z1 into Z2 is 4, the energy minus 3,795 kilojoule per mole, and for Al2O3 there is a charge Z1 and Z2 is equal to 3 into 2 is equal to 6, that is 15,269.9 kilojoule per mole. Lithium fluoride, there is a minus 1033 kilojoule per mole. The crystal structure, if you consider, the increasing the coordination number of a given ion in a crystal lattice would increase its lattice energy. For example, in sodium chloride crystal lattice, each sodium ion is surrounded by 6 Cl minus ions. Therefore, the coordination number of Na plus or Cl minus in NaCl lattice is a 6. The cesium chloride lattice, the coordination number of an ion is a 8. The numerical value of Madelung constant of the cesium chloride is the highest, 1.7627, than for the sodium chloride lattice is 1.7476. Means cesium chloride has value 1.7627, and the NaCl has value 1.7476. It is value of the Madelung constant. Thus, for equal interionic distance, the cesium chloride type of lattice is about 1% more stable than the sodium chloride lattice. Then electronic configuration. The electronic configuration of cations also affects on the lattice energy of their compounds. Copper plus 2, zinc plus 2, Ag plus, Au plus and Hg2 plus have the D plus configuration. The lattice energy increases in a molecule having cations with a D raised to 10 configuration. Cations with a D raised to 10 configuration, D10 configuration, are formed by the transfer of their NS electrons to the non-metal, thereby converting it into an anion. Example, copper plus ion is formed by the transfer of its 4s1 electron to chlorine when it forms the copper chloride. The cations with the D10 electrons, for example, the atomic number 29, the ion copper plus 2 is the last 3D10. Another, that is a 30, zinc plus 2, the last electronic configuration of that ion, zinc 2 plus 3D10. Then 47 atomic number of silver Ag plus, the last electronic configuration the 4d10. Then 79 Au plus gold ferric plus 79, the last electronic configuration 5d10. Crystalline sodium chloride is more stable than its gaseous atoms or gaseous ion pair. Delta E is negative. Energy is evolved when solid sodium chloride is formed from its gaseous atoms Na plus and Cl minus ions in a gaseous state. Thank you.